Back in the 1960s, NASA had this, well, let's call it an astronomical problem. And I mean that literally. They had to get astronauts to the moon and back, but a huge piece of the puzzle was just missing. This is the story of a surprisingly elegant algorithm that cracked the whole thing wide open. No, seriously, just think about that for a second. When you're out there, between worlds, how do you even know where you are? Or more importantly, where you're headed? I mean, it's not like you have Google Maps up there. There are no roads, no landmarks, nothing. You're trying to hit this tiny, moving target 250,000 miles from home. If you're off by even the smallest fraction, you don't just miss your exit, you miss the moon completely and just drift off into the void. This was the massive problem facing the Apollo program. So to tackle this thing, the engineers at NASA's Ames Research Center knew they needed a totally self-contained onboard navigation system. But here's the kicker. The data they had to work with, it was a mess. So NASA was stuck between a rock and a hard place. On one hand, you've got the spacecraft's own internal system, which is constantly giving you updates on your position. Think of it like a wristwatch. The problem? The watch runs just a little bit fast. And over a few days, those tiny errors add up until you're thousands of miles off course. On the other hand, the astronauts could literally look out the window and take readings from the stars. This is like checking a super accurate clock at a train station. It's perfect in that moment. But you can't do it all the time, and the measurements can get a little shaky, a little noisy. So you've got these two flawed sources of information, and you have to somehow blend them together to get one single reliable answer. How do you even do that? Now, the engineers weren't starting from scratch. They tried using stuff that worked for missile guidance systems back on Earth. But flying to the moon isn't like guiding a missile. The physics, the orbital mechanics, it's not a straight line. It's what they call nonlinear. It curves and changes. And those star sightings, they're just individual snapshots in time. The old tools just broke. They were not going to work. They needed something totally new. And you know what's crazy? The breakthrough didn't come from some giant top-secret NASA project. It came from a total chance encounter. Just the right idea, finding the right people at the absolute perfect time. So an engineer over at NASA Ames gets this idea to invite a researcher, a guy named Rudolf Kallman, to come give a talk about a paper he just published. And as Kallman is up there explaining his theory, you can just imagine the engineers in the room who'd been tearing their hair out over this navigation problem. Their jaws just hit the floor. They realized, wait a minute, this could be it. This could be the answer. Yeah, there was just one tiny problem. Kallman's paper was, well, it was practically unreadable for a regular engineer. It was super dense, totally abstract, filled with math and notation they'd never seen before. A NASA report from the time even said it was very difficult for practicing engineers to grasp. It was like they'd been handed the key to the universe, but they had no idea how to even put it in the lock. And that's where an engineer named Stanley Schmidt comes in. He had this total eureka moment. He realized, hey, wait a second, we can take Kallman's linear ideas and combine them with stuff we already know how to do to make it work for our big, messy, non-linear space problem. This was the moment. This was the bridge from abstract math to a real-world solution. Okay, so with that breakthrough, the team at Ames just went for it. They immediately started building a massive digital simulation to prove this thing could actually work. It was time to turn this beautiful theory into a real tool. So what is this Kallman filter anyway? Well, at its core, it's just a brilliant way to mash up data from different sources. It's designed to take a whole stream of measurements that are all a little bit wrong, a little bit uncertain, and spit out a single estimate of what's really happening. And the crazy part is, the more messy data you feed it, the more accurate it gets. The real magic, the secret sauce, is this simple two-step dance it does over and over again. First, step 1, predict. The algorithm makes an educated guess. Based on where it thinks the spacecraft was a second ago, and the laws of physics, it predicts where the spacecraft should be right now. Then, step 2, update. It takes a brand new measurement from the real world, like one of those star sightings. It looks at its prediction, looks at the new data, and says, okay, I was a little off. And it corrects itself. It's this constant loop, predict, measure, update. And with every single loop, its guess gets better and better. In that two-step process, I know it sounds simple, but that decomposition was a huge deal. See, Kallman's original paper kind of assumed you had this constant fire hose of data. By breaking it into this predict-update cycle, the NASA engineers could now feed it data whenever they got it. This is what made the theory actually usable for a real space mission. But they weren't done yet. Not by a long shot. To really nail the crazy physics of flying in space, they had to add one more brilliant tweak. So check this out. Instead of having the algorithm always try to get back to some perfect flight path planned months ago, they changed it. At every single step, the algorithm would recalibrate based on its own last best guess of where it was. The logic was genius, really. Why try to get back to an old plan? The spacecraft is probably way closer to where the algorithm just calculated it was. This modification was so important it got its own name, the extended Kalman filter, and this is the version that really went to the moon. I mean, it is just incredible when you stop and think about what this small team pulled off. They took this super abstract theory, they bent it to work in a nonlinear world, they invented the extended Kalman filter, they reformulated it into a practical predict-update cycle, and then they built a massive simulation on a clunky old IBM 704 computer to prove the whole shebang would actually work. Unbelievable. And the simulation? It worked. The results were crystal clear. It proved, for the first time, that a completely self-contained navigation system right there on the spacecraft was actually possible. The impossible problem? It finally had a solution. But of course, this story doesn't end in space. After it got us to the moon, this incredible piece of code came back down to Earth, and it quietly changed, well, pretty much everything. Because it turns out that basic problem, blending noisy, messy data together to find the truth, isn't just a space problem, it's an everywhere problem. Right now, the smartphone in your pocket is solving the exact same problem the Apollo guidance computer was. Your GPS signal? It's noisy and can be inaccurate, just like those star sightings. The little motion sensors inside your phone? They drift, just like the Apollo inertial system. And what's sitting in the middle, fusing all that bad data together to put that little blue dot perfectly on the map? You guessed it, a Kalman filter. And its use today is just mind-blowing. We're talking about everything from guiding drones and self-driving cars to helping robots make sense of the world around them. It's used in economics to forecast trends. It's used to control massive power grids. The Kalman filter is, without a doubt, one of the most important algorithms ever written. It is the invisible engine running behind so much of our modern lives. And that just leaves us with this one kind of cool final thought. This whole idea was created to find a clear signal in the empty vacuum of space. But today, we're not in a vacuum. We're drowning in a sea of messy, imperfect, noisy data. So the real question is, where is this elegant 60-year-old idea of predicting and updating gonna take us next?